All right, this is the second video on section 2.2, and we're looking at determining volumes by slicing. In this particular video, we're going to be using what's called the disk method, and with the disk method, you're going to be slicing up into a bunch of disks. You're going to be adding up the volumes of a bunch of disks. The volume of a disk is pi r squared w, where r is the radius and w is the width. So we'll draw a disk like this. Okay, there's the radius r and then the width w. So it's really just a cylinder, a regular cylinder. And so what we're going to do is we're going to take this will be, for example, on the x-axis here, we're going to take a rectangle, okay, of a width of delta x and a height of r. And then we're going to rotate around the x-axis. And so we'll rotate that around, and that's going to form a disk, and hence the name, the disk method. So we're going to look at first rotation about the x-axis, then we'll look at rotation about the y-axis, then we'll do an example where we rotate about the x-axis and the y-axis. Okay, so when we're doing a rotation about the x-axis, the radius, and then I'm going to call it a representative rectangle. I don't think I said representative, I said represented. Representative. A representative rectangle are perpendicular with the x-axis or any horizontal line. If you're rotating around a horizontal line, your functions are going to be perpendicular to the x-axis. And also your functions will be in terms of x, and you'll be integrating in terms of x. Okay. Alright, so there's our function f of x. That will also be our radius function. And we'll go from a to b. And then we'll go ahead and highlight the region that we're going to go ahead and rotate around the x-axis. Okay. And then I'm going to go ahead and draw in a representative radius. So that's going to be, it's not as important here, but it does help me determine the heights of my rectangles here. It's going to be more important when we get into the washer method of figuring out the outer and the inner radius. And the radius will always emanate from or start from the axis of revolution and hit the outer edge of the figure in the case of the disk method. Okay. All right, then we'll draw a representative rectangle. That's what we're going to rotate, a width of delta xi, and the height of r of xi with some sort of partition here that we're going to use. We're going to use a Riemann sum. Okay, and then we're going to rotate that around, and that's going to give us a disk. Okay. Now this image over here is from the OpenStax textbook, and so we start with a region in the xy plane, and this looks like they're going to rotate around the x-axis, so you can see a partial rotation so far. So you have a partial rotation. And then over here you have a full rotation around the x-axis here. Okay, and so that's what we got going on over here. It's just I've only sketched a little bit of it. You know, you're gonna have another disk here and another one here, etc. And it's gonna keep going. So the formula for calculating the volume of revolution using the disk method is we're going to take the pi r squared. Okay, we're going to take the pi r squared, and then we're going to multiply that by a delta x, which is going to give us a little bit of a thickness. So then that brings us into the 3 dimensions. We have a volume, and so the pi is a constant. So we'll slide that out of the integral. Okay, so for our disk method, the volume is going to be pi. Integral from a to b, because the radius is variable and it's going to be dependent on where the x is, there's your r squared and then dx. Okay, and then again that's your r of x, that's your kind of your height function of your rectangles, or that's your radius. Okay, so you got the pi r squared. That's the area of the circle, give it the dx, that gives us a little bit of thickness, and so you're finding volume of a disc, or you call it a cylinder also. Okay, let's go ahead and do the setup for the generically how we would go about the y-axis, and then we'll go ahead and do an example. So we'll look at rotation about the y-axis. So we're rotating about the y-axis, the radius, and let's see, did I do it again? Oh, I said it right this time. Representative rectangles are perpendicular to the y-axis, and the radius functions must be in terms of y. So we'll do an example here. So we'll draw a continuous function here, call it f of y at some point in time. So we're going to integrate from c to d. That's the region that we're looking at. That's the region we're going to rotate. Okay, and that's f of y. There is a radius function, and r of y and f of y are the same thing here. So notice again, it starts at the axis of revolution. So I think I'll draw this in a little bit later. So there you're rotating around the y-axis to the outer edge of the figure. Okay. Here's your representative rectangle with a thickness of delta yi and a radius or a height of delta of r of yi. Okay. I'm just going to rotate that around. And then again, volume is pi r squared, but because we have variable radii, it's going to be pi integral from c to d, r of y squared dy. Okay. All right, so let's go ahead and work out an example here. Speed it up a little bit. All right, so find the volume of the solid formed by rotating y equals negative x plus 5, bounded by x equals 0, y equals 0. And then we're going to rotate it in part A about the x-axis, and in part B, we're going to rotate it about the y-axis. So for A, we'll go ahead and draw a rough sketch. So again, it's important to draw sketches. Okay, doesn't have to be a beautiful sketch, just a decent sketch. Rotate around the x-axis, go ahead and highlight the region that we're going to rotate, determine your radius function here, which is simply the negative x plus 5. Your volume is going to be pi, integral from a to b, r of x squared dx, okay? So we got our radius function, and then our limits of integration are going to go from 0 to 5 along the x-axis. So pi, integral from 0 to 5, negative x plus 5 squared dx is equal to pi, integral from 0 to 5, FOIL that out, x squared minus 10x plus 25 dx. Integrate it, so we have pi times x cubed over 3 minus 5x squared plus 25x, evaluated from 0 to 5. So that gives us pi 125 over 3 minus 125 plus 125. And so that is going to be 125 pi over 3, or approximately 130.9 units cubed. Okay? So that is rotating around the x-axis. We'll go ahead and look at rotating this around the y-axis. Okay, so rotation around the y-axis, it's going to be the same region. But now our radius function is going to come from the axis of revolution, and that needs to be a function of y. So if we say y equals negative x plus 5, if we solve that for y, x is equal to negative y plus 5, that's going to describe the distance from the y-axis to a point on the line there. So that's our r of y. So r of y is equal to negative y plus 5. Volume here is going to be the integral from c to d, pi times the integral from c to d, r of y squared dy. So pi, and then we're going from 0 to 5, so it ends up being the same there. So limits of integration are 0 to 5, and we're looking at the y-axis for those. Okay, negative y plus 5 squared dy. Now this is the exact same integral as the previous one, so we have some nice symmetry going on. So we're going to end up getting the exact same volume here. So this is the exact same integral, other than it's y instead of x. So pi integral is 0 to 5, y squared minus 10y plus 25 dy. So that's pi. Y cubed over 3 minus 5y squared plus 25y, evaluated from 0 to 5. So it's going to be pi 125 over 3 minus 125 plus 125, which is going to give us 125 pi over 3, or approximately 130.9 units cubed. Okay. All right, so we'll go ahead and do, I think, 2 more videos. So the next video will cover the washer method, and the washer method is very similar to the disk method, very similar. And then I think we'll do an example of the washer method, and then I think I have one more video that has a couple of extra examples. Okay, so we'll see you next time.